Hello, this is Dr. Michael Hassan, the Engineering Doctor, and this is lecture number 43, Synchronous BCD Counter. Of Chapter 7, Counters and Registers of the course Digital Logic Design or Digital Systems or Digital Electronics. This slide is a disclaimer for you to read. I cite 3 references in this lecture. However, there are many books in digital logic design. In this lecture, we are going to cover Synchronous BCD Counter, which is highlighted in the color red. What's a BCD counter? A BCD counter counts in binary coded decimal from 0000 to 1001 and back to 000. It is also known as a decade counter since it counts 10 states. Therefore, a BCD counter does not have a regular pattern in straight binary count because of the return to 0000 after a count of 1001. To design a BCD counter, we follow the design procedure as discussed in previous lectures. Now, since we have 10 states, 4 flip-flops are needed. Okay, because with 3 flip-flops, we have only 8 states. With 4, we can have the maximum of 16 states, but here we need only 10 states. Now, if the counter starts with any state outside the range from 000 to 1001, okay, the counter, we have the option to use don't care, or we have the option to choose one state like the reset state, 0000. Of course, choosing don't care will simplify the hardware of the counter. So you may get counter with much less hardware, as you can see in the next slide. So the state graph of the counter, if we are in state 0000, we go to 0001, we can call this, name it as 0 to S1, to 0010, 0011, and all the way back to 1001, then back to 000. Now, how about if I have a state after the 1001, like 1010? So I can go to next state is all don't cares. I don't care where to go. But design like this, when you design with don't cares, you will risk actually the possibility of generating another loop. So the counter, if it enters another loop, a false loop, the counter will be a failure in the design. On one hand. On the other hand, if you go all those unused state, the present state to the reset state, each one goes to 000, you may get very complicated hardware or very more gates to use. You must use more gates or more hardware to generate the excitation inputs for each flip-flop. Okay, so it depends on your design. I prefer to use don't cares than test the counter, to analyze the counter and see those don't care states what they end up to be. Okay, so the 1010, for instance, if you start, where it's going to end up to be, at what state, and whether those don't cares happened that they will generate a false circle or a false count for the counter and may get trapped into another circle of states. So once we have the present state and the next state, we can draw the Kmaps. If we are designing with JK flip-flop, we can draw the Kmaps for A+, B+, C+, and D+. And we use the shortcut method, the beautiful method. We will divide the map to 2 portions. Once the A prime or A equals to 0 map, as you see here, and the other A is equals to 1 map. For A equals to 0 map, we will group the ones. Okay, as many ones as possible. Since we have only one term with a value of 1, so we group it, and will give me BCD. Why didn't I take the A prime? Because the A prime is the coefficient from the characteristic equation. A plus is equal to JA prime. So I am in the A prime map. So the map is downgraded from 4-variable to 3-variable map. So the A is fully ignored. So we can ignore the A. So it is really, so this midterm can be represented by BCD. BCD. How about Ka? So we go to the A equals to 1 map, or the A map, okay, and we'll simplify for the zeros to get K. If we group the ones, we will get K prime, okay? So we simplify, so we have group 4, and the 0 will cancel with the 1 for B, and the 0 will cancel with the 1 for C. So what I will have D. So Ka will be D, okay? So JA will be BCD while KA is equals to D. And this is a very correct answer. Very correct answer. We do the same thing with the B plus map. With B plus map, we'll go to the map to B equal to 0 map. Now B equals to 0 map will be this column and this column, the 0, 0 column and the 1, 0 column, because both of them has B0. Okay, and we group for the ones. And we have only a group of 2. This don't care with this one, we'll group. And those 2 will give me the 0 will cancel with the 1 for the A. I don't care about the B because I am in the B0 map. So A will be cancelled out and I will get CD. So JA, the JA map will give me CD. CD and JB will be equals to CD, which is the correct answer. The same thing, we go to the K prime map or the B equals to 1 map, and we group the zeros, and I have only 2 zeros. Again, 0 will cancel with the 1 for the A. I am in the B equals to 1 map, and this is also equals to CD. So KB will be also equals to CD. So very interesting. And we find that JB equals to CD and KB equals to CD. So we can use only one AND gate for both, right? The same thing, we go to the AE, to the C plus map, and we group the map to C equals to 0 to find JC, and to C equals to 1, which is the lower 2 rows, to find KC. We group the ones for J, and we have the 1 will cancel with the 0 for B, and what we will have? We will have C prime D. But C prime is the coefficient, so JC will be equals to D. JC will be equals to D. Oh, JC will be equals to D. JC, it is true. We have the 0 will cancel with the 1. Okay, 0, we forgot an A prime. The 0 will cancel with the 1 for the B, so we will have A prime D, A prime D, A prime D, which is very correct. So JC will be A prime D. So we don't forget the horizontal side of the map. The same thing, we go to the C1 map, which is the lower 2 rows, and we have a set group of 4. So everything will be cancelled vertically. So what I will have CD, but C is the coefficient. We are on the C1 map, so we ignore it. So KC will be equal to D. KC will be equal to D, which is very correct. So now we go to the D plus map. The D plus map, we divide it to D equals to 0 and to find JD, and D equals to 0 in the upper row and the lower row will give me the map for D equals to 0. So we will ignore, so we group all the ones. When you group all the ones, everything grouped up. Horizontally, everything will be cancelled out. Vertically, the 0 will cancel with the 1 for the C. So what I have nothing than 1 times d prime. D prime is the coefficient, so I have only 1. So JD will be equals to 1. The middle, the center 2 rows, will be d equals to 1. So I have to group the zeros to give me KD. And grouping the 0 again will give me only 1. So this will end up with JD equals to KD equals to 1. See, the shortcut method is so simple, so easy, straightforward. So we found the answer. And once we have the answer, we can draw the counter logic network with JA and KA is D, JA is BCD. Okay, we have all the variables that we need. We have the output A, B, C, and D. And we have A prime for JC. We need A prime and D. A prime is right here. We need CD for the AND gate to JB and KB. And we have the complete circuit. And JD and KD will be connected to logic 1. And so we designed a BCD counter using JK flip-flops, okay, with no hassle, and we use the shortcut method to do that, which is a very interesting method as well. It makes the life much easier for us. Now, this is the end of this lecture. I thank you so much for listening. Please subscribe by clicking on the blue circle. And see you very soon in the next lecture. Sincerely, Dr. Hassan.